Comparison among 3 nations: insulin resistance versus 4 diseases prevalence percentages. Number 1237, VMT Sharp 622, March 31, 2025, by Gerald C. EclaireMD Foundation. Category: Insulin resistance and methodology. Key messages. The author investigated the direct relationships between insulin resistance measured via fasting plasma glucose, FPG, and 4 disease conditions: type 2 diabetes, T2D, cardiovascular disease, CVD, chronic kidney disease, CKD, and dementia, including both Alzheimer's and Parkinson's diseases. The data used in this study were drawn from public health sources in 3 nations: the USA, Japan, and Taiwan, spanning a 15-year period from 2010 to 2024. Naturally, the degree of cleanness and completeness of these public domain datasets depended on the specific databases accessed by the AI search engine. The author performed certain manual data verification and minor data correction where necessary. This public health study incorporated 2 distinct research methods. The first involved traditional statistical tools, including average values and correlation analysis between paired variables. The second utilized the viscoplastic energy model, VMT, developed by the author as part of his math physical medicine, MPM, methodology, reframing the role of viscoplastic energy in modeling disease dynamics. The GH method, math physical medicine, transforms complex biological realities into quantifiable, time-dependent models, much like how differential equations describe motion or wave functions capture quantum behavior. At the heart of his MPM method lies the principle of viscoplastic energy, VMT model, a cumulative measure that reflects internal resistance, system response delays, and nonlinear transitions between FPG, fasting plasma glucose, and the prevalence of 4 conditions: T2D, CVD, CKD, and dementia. Unlike static statistical models traditionally utilized in medical research, this VMT approach tracks the gradients, curvature, and temporal mismatches that arise across years of biological change. While the model does not explicitly label variables such as genetics or lifestyle, it inherently captures their influence through real-world data curves. National differences in FPG and mortality disease relationships are shaped by factors such as dietary and exercise habits, healthcare access, and population aging. These variables are already encoded in the mathematical behavior of the system. For example, Japan's higher viscoplastic energy compared to Taiwan, despite having healthier absolute prevalence rates, reflects internal systemic and nonlinear curve mismatches, not research model failure. This is a strength of the approach, not a weakness. Moreover, the author's collected data indicates that epidemiological frameworks often depend on population averages, categorical assumptions, or cross-sectional snapshots. In contrast, the viscoplastic energy model provides a longitudinal, quantitative tool that respects the continuous nature of disease progression. It reveals insights that conventional statistical methods often miss, such as hidden time lags, inflection points, or resistance patterns between metabolic input and clinical output. In sum, the math physical VMT model does not ignore complexity, it distills it. It offers a bridge between biology and physics, biochemistry and math physics, providing a new telescope-type lens to understand, predict, and ultimately manage the burden of chronic diseases across populations. Here, the author would like to offer some more explanations of certain terminologies and concepts. 1. Refine certain terminologies. In this model, the term stress-strain curve represents the dynamic relationship between a physiological input, e.g., FPG, and the system's observable response, e.g., disease prevalence. A smoother curve indicates a proportional, synchronized reaction between metabolic dysfunction and disease progression, while a sharper or mismatched curve suggests internal delays, resistance, or nonlinear behaviors within the biological system. Similarly, internal system resistance refers to the body's tendency to buffer, delay, or modulate the onset of clinical symptoms in response to rising metabolic stress. This resistance may stem from genetics, lifestyle, early interventions, or other compensatory mechanisms that delay disease expression, despite increasing FPG levels. 2. Clarify the VMT mechanism. The viscoplastic energy, VMT, model calculates cumulative energy as a function of the mismatch between FPG as input and disease prevalence as output over time. It uses the area under the stress-strain-like curve derived from the time series of these variables. Sharp deviations, delayed responses, or nonlinear trajectories between FPG and disease prevalence result in higher energy accumulation, analogous to how physical energy builds up in a viscoplastic material under prolonged or irregular deformation. This energy serves as a quantitative marker of systemic burden and internal friction in disease development. A specific case study, Taiwan, Japan, and the United States. At first, the author calculated 4 correlation coefficients for each nation, comparing FPG data with the prevalence percentages of T2D, CVD, CKD, and dementia across the 3 countries, the USA, Japan, and Taiwan. All 12 correlations, 4 diseases multiplied by 3 nations, were exceptionally high, each exceeding 97%. This strong statistical result indicates that insulin resistance, as measured by FPG, is highly correlated with the development of these 4 chronic diseases in all 3 countries. Secondly, the author calculated the total viscoplastic energy, VMT, between FPG and the 4 disease prevalences, T2D, CVD, CKD, and dementia, for each of the 3 nations. Taiwan, 172, baseline 1.00, Japan, 219, 1.27 of Taiwan, USA, 1030, 5.98 of Taiwan. It is clear that the total VMT energy for the USA is 5.98 times higher than that of Taiwan, while Japan's total is 1.27 times that of Taiwan. The total VMT energy represents the summation of 4 component energies, each corresponding to one of the disease conditions, T2D, CVD, CKD, and dementia. A special note discovered using viscoplastic energy method. Using statistical tools alone to examine epidemiological data, one might conclude that the Japanese case is superior to the Taiwanese case. However, using the viscoplastic energy method, the findings differ. While the high energy in the US reflects greater fluctuations and higher disease prevalence, the surprising result is that Taiwan's energy is 27% lower than Japan's. Even though Japan is healthier by all 4 disease metrics, this difference can be explained by the mechanics of the author's viscoplastic energy model, VMT, which responds not only to absolute values, but also to how FPG and disease prevalence trends interact over time. 1. Viscoplastic energy captures mismatches and curves. The VMT model accumulates energy when there is misalignment or resistance between the input, variable, FPG, and each output, disease prevalence. Even if Japan is healthier overall, it might show sharper curvature, steeper transitions, or nonlinear lag between FPG and its 4 disease prevalences. Taiwan may have a more linear and synchronized trend of FPG rises, and diseases rise accordingly. Japan, on the other hand, may experience a delay or resistance in disease response, despite elevated FPG, which builds up internal energy, like a viscoplastic material resisting strain. 2. Healthier populations can show more internal resistance. Japan's lower prevalence does not imply low energy. If the population resists disease progression in response to elevated FPG, due to better interventions or genetic factors, this resistance itself generates energy in the model, just as stiffer materials store more energy under deformation. 3. Taiwan's trends might be smoother. If Taiwan's FPG and disease prevalence have risen together in a steady, proportional way, the stress-strain, input-output, curve, would be smoother and generate less viscoplastic energy. Japan, even with lower disease rates, may have had inflection points or curve mismatches over the years, e.g., slower rise early on, sharper rise later, resulting in higher cumulative energy. 4. Aging and dementia curves in Japan. Japan has a larger super-aged population, especially those aged 85 and above, which skews dementia and CKD prevalence upward in later years, even if earlier years show healthier patterns. A sharp upward curve near the end of the timeline can cause a spike in energy due to high curvature in the FPG-dementia relationship. For example, Japan's FPG versus dementia energy is 51.3 versus Taiwan's 23.45, which is 2.19 times higher. In comparison, Japan's FPG versus CVD energy is 48.3 versus Taiwan's 39.2, 1.23 times higher. But, Japan's FPG versus CKD energy is 90.30 versus Taiwan's 76.65, 1.18 times higher. 5. Summarized explanation. Taiwan has higher disease prevalence, but shows more direct, linear correlations between FPG and health outcomes, meaning less internal resistance and therefore lower energy. Japan, while healthier overall, displays more nonlinear response, resistance to disease, progression, and curve mismatches, which the VMT model interprets as higher stored energy.